All right. Hans Eysenck was the first person to really kick off this biological approach. Um, but he was actually working on things that you would consider to be from the trait approach before kicking off the biological approach. So, if you, when learning about him, think, wow, he sounds like he's kind of a trait approach guy. Looking at this first part of the slide, that's true, but you're going to see that he really started on some very important basic things, research on physiology. First person to do that, in the biological approach, so that is how he is classified. But let's look at his major contributions here leading up to and including that. Hans is our super trait guy, and I want you to think back now to before Gordon Allport actually came up with after Gordon Allport came up with these 4,000 plus personality traits and this idea of studying personality this way. But before they figured out factor analysis and how to use that to figure out what the big ones were, Hans Eysenck was really interested in this, and he was working in this. And he predicted that there would be 3 super traits. Okay? He predicted that when we had a way not only of figuring out what he called super traits were, what we now call the big traits, okay, and had a way of studying their genetic influences. He said these 3 would be the super traits, and they would have a larger genetic component, inheritability component, than the others would have. So they would be more significantly inherited from your biological mother and father. And you see, he hit 2 of them right on the nail, right on the nail head. So extroversion and neuroticism. And what's interesting is he wasn't actually wrong about psychoticism. You may or may not know what psychoticism is. Someone who is psychotic is cold, uncaring, unconcerned with the rights of others or the consequences of their behavior on others. And so that is more of an abnormal trait, right? Most people, that wouldn't describe most people. And so he wasn't really wrong. It's just that the big 5 were measured in normal populations. So when you take the big 5 personality test this semester and give it to someone else, it's measuring normal things. So no matter how high or low you or the person you measure comes out on anything, you can't say, look, there's something wrong with you. We're not measuring abnormal at all with that scale. That is for normal research. That's for research within normal populations. All right. Now, Hans Eysenck, besides predicting 2 of the big 5, he also laid out a roadmap. Here Gordon Allport had come up with this idea. Why don't we use these personality traits and find a way to measure each one and figure out what the big ones are, at least. We can't measure 4,000 of them, but find out what the big ones are, and then, measure people using the same continuum for each trait. It varies between traits, okay? But the same continuum for a particular trait, and then, we can use that, to predict behavior. Well, Hans was one who spelled out a roadmap of how you would do that. And so he proposed a trait hierarchy, which is certainly has shown to be true. Okay? He said that the super traits would be on top. So now you can think of the big 5 being on top, right? And then, with each of these big 5, so we'll just look at one of them, extroversion. He said there are many traits that are going to be part of that. That big, when we say extroversion, we're talking about a whole cluster of traits, right? Hey, in that extroversion cluster. Hey, so for instance, one of them would be outgoing and one of them would be sociable. right? But he said there's many, many, many of them. And for every single trait in that cluster, there's also, that is linked to many different habitual responses. So if you were trying to draw out this graphic, keep getting wider and wider, start out with just one trait. The second row would be, 6 or more traits. And then the third row would really be exponential. Because there are so many different habitual responses associated with a trait, and even more specific behavioral responses. Okay. He said this is how you can predict behavior once you know people's differences on the scale and what your big 5 traits are, your big traits. He didn't know there would be 5. So what you do is you start with that super trait and the traits, and then the habitual responses. Now, we gave examples of extroversion traits being sociable and I forget the other one. Anyway, sociability, let's work with that. Okay, there are many different habitual responses that are linked with sociability, and one of them is likes to be around a lot of people, right? And then a specific behavioral response that would be related to that. One of the many would be, going to a party where there are a lot of people. And so you could predict a specific behavior in the future, okay, and see how well your personality trait predicts it between individuals. If they were all invited to a party where there would be a lot of individuals, you measure the personality traits and see if their score helped to predict that. Okay. Now, I think that Hans' most valuable, most exciting contribution to the study of personality was to kick off the whole ball game in looking at physiology. Okay. And what he predicted and then showed was differential sensitivity to stimulation. And I'm going to give you right now the example of coffee, and then we'll look at some more when we look at research in the second part of the behavioral approach. Not the second segment, but the second part, so series of segments. And what he showed here that is so very interesting is a difference between introverts and extroverts. Introverts and extroverts have different physiologies, and that makes them have different sensitivity to the caffeine in coffee. So if you happen to be an extrovert, you can drink a lot more coffee before you feel an effect from it than an introvert. So you have a tendency to drink more coffee. And sometimes introverts are so very affected by coffee that they don't like to drink it at all. But there's very different sensitivity to caffeine. And he studied this in some really interesting physiological ways. And we'll go into some of those methods also when we get to the research part. Okay. But before we do that, okay, we are going to move on to Buss, our second theorist here. And actually, before we go to Buss, you need another crash course on something. So many of you are already familiar with evolution and the terms like natural selection, what that means. Okay? But we want to make sure that everybody is up to date here. Very important to understand Buss's contribution here to the study of personality. So natural selection, we're talking about here is that sometimes what we tend to see is instead of people varying over a trait with our normal distribution, okay, understand that we talk about traits here, we're getting a far broader definition of trait than those 4,000 that Gordon found in the dictionary, because those what we call personality traits, okay, are normally distributed. But remember from a trait approach, and later on, especially when we hit some of the other approaches, that trait, the term trait by itself, is used in a more broad way. So it includes other things like preferences. And so, some of our preferences we differ on, but some of them tend to be the same within a population, or at least the same within a gender within a population. And those we call universal traits, okay? And when we see something like that, you can trace it back and you can look at how that particular trait would, or preference you might think of, would actually make it more likely that somebody would pass on their genes, okay? In other words, those genes have been the ones that were more successfully passed on until they've become universal within a species, or at least within gender within a species. We call those universal traits. As an example of that, okay, what I want you to do is don't memorize, don't write these down, but just get them in your head, okay? Because we're going to use 3 symbols on the next few slides. Just X's, Y's, and O's. And X is just going to symbolize men who prefer mating with women of a fertile age. Okay? Y is going to symbolize men who prefer mating with women over a fertile age. And O is going to symbolize men who prefer mating with girls, in other words, under a fertile age. Okay? Females under a fertile age. So here's the deal. So just get those symbols in your head, and I want you to imagine a population towards the very beginning of time of human beings, okay? And let's say it was this small, okay? And we're just looking at men here, okay? But let's say it's this small. And you see that the distribution could have started out varied across these 3. Okay, right now, you know that that would be a very different story. But let's say it started out this way. Now, it takes a few generations for evolution, natural selection to do its thing. But tell me this, the next few generations down the road, okay, or even the next generation, what do you think it's going to look like in this distribution? So, is there one particular symbol that is going to be more likely to pass on genes, so that one's going to be heavier? So just so that we can see the percentage really well, we're not going to indicate the average, which was a lot more than 2.5, but the average expansion in the population, number of kids they would have. But instead, we'll look at the same number and just look at the percentage. So probably looks something like that, right? Now, instead of being evenly distributed, you see that the X's have an advantage. And then over time, you'd expect it to start looking more like that. So that X advantage has grown, right? Men who prefer mating with women of a fertile age are going to be more successful in passing on their genes. And, even if they don't always do so, the thing is, sometimes Y's and O's are passing on their genes because that in life you don't always get what you want, right? That's a lesson we've all learned so well. But, they're going to certainly be seeking that out. And so they're going to be less successful than the X's. And then, as you look further over time, it's going to look like this and this and this until finally, what do you have? You have a universal trait within gender. So, now let's review this. Okay, so natural selection, traits that have a reproductive advantage are more likely to be passed on. That's it. That's it. Traits that have a reproductive advantage are more likely to pass on. And so they're going to become universal in a species. Okay? But genders often face different problems. And so some naturally evolved traits are universal within a gender. So women face different reproductive environment, different set of problems than men do. And so the one that we looked at was a universal trait within gender. Okay. And now we're ready for David Buss, so we will start with that with the next lecture segment.